A very good evening to all of you. So today we will start our discussion on the high frequency analysis of the BJT. We have already studied the small signal analysis of the BJT, and there we have done the AC analysis. So you know that this circuit is a voltage divider circuitry, and this circuitry is going to provide the bias stabilization. But if you want to amplify any AC signal and that signal is if it is very weak, then the first stage of the amplification will be the voltage amplification, and in that case you will have to use a small signal amplifier. So when you are going to use a small signal amplifier, so that time you will have to place this blocking capacitor, that is CC1, CC2 and CE. Now this CE is the bypass capacitor. So this CE is connected across the bypass resistances. Now these CC1, CC2 and CE, they are externally connected they are externally connected capacitances, and there are some internal capacitances also. We have already have a discussion on this stray capacitances. Now there is a CBC, that is called a transition capacitance. CBE is called a diffusion capacitance, and there is one more capacitance between the collector terminal and the emitter terminal. So we will have a discussion on these capacitances, if they how they behave at a low frequency and how they behave at a high frequency. So if you are operating your system at a low frequency, that means F will be equal to 0, or you can say F will be tending towards 0. So when F will be tending towards 0, then Xc will be tending towards infinity. And in that case, your capacitors will be open circuited. So when you operate your circuit, so this capacitor is not going to provide any harm to your operation, and then you will be having a good gain. So this coupling capacitors, stray capacitances, all will get open circuited. But when you are going to operate at a high frequency or at a very high frequency, so when I talk about a high frequency, it means that this capacitor, that this blocking capacitors and the bypass capacitor, they are having a value of the order of microfarad, and these stray capacitances, they are having a value of the order of picofarad. So you can just see the difference between the two capacitors. One capacitor is having a very high value, while the other one is having the low capacitance, and that is going to play a game. So when you are operating at a very high frequency, then these all these capacitors will be short circuited, because at a high frequency Xc will be tending towards 0, so it means they will be acting as a short circuit. But when I talk about the high frequency only, so these blocking capacitors and the bypass capacitors will get short circuited, and they will, and these stray capacitances, or you can say a parasitic capacitances, they will exist. So in that case, you will have to find the cutoff frequency. You will have to find the cutoff frequency that beyond which, if you operate your transistor, so then there will be a decrease in the gain, and below which if you operate, then you will be having certain finite gain, and that gain will be AV will be equals to V2 upon V1. Now what is V1? V1 is the input voltage. Then what is A? A is the gain of the amplifier, and V2 is the output voltage. This we have already discussed. So now this circuit is a full of capacitors and the resistor. So what we can say, that frequency at the cutoff frequency is a function of the capacitor reactance, because resistance is a frequency insensitive element, whereas capacitor reactance is a function of the frequency, that is Xc will be equals to 1 upon 2 pi Fc. So it means that you will have to evaluate this cutoff frequency. So if you just trace the gain, that gain will be reduced by minus 3 dB. Suppose it is at this point it is 20 dB. So at this value it will be around 17 dB. The bandwidth will be the range of frequencies for which the gain is constant. That is called a bandwidth. And our requirement is the finite gain only. So this is all about the gain versus frequency. So now we will have to we will have to determine the high frequency model for the BJT. So how you are going to find? Now you see here, The blocking capacitors and the bypass capacitors are in microfarad, whereas the stray capacitances are in picofarad. So it means that if you want to obtain the equivalent model, then you will have to do the AC analysis, because ultimately high frequency means what? That is the AC analysis. So in that case, you will have to replace this transistor by some model. We have already discussed the three types of model of the BJT. The first one is the RE model, then second one is the RPI model, and the third one is the H parameter model. So in the RE model, there will be beta into RE. You can see here beta into RE will be there, and the beta into IB. So it means that we have replaced the entire transistor by a simple RE model. That is a common emitter configuration, and that common emitter configuration has been replaced by the simple RE model. We have already had a discussion on this RE model. So now, if you want to do the high frequency analysis, it means that this DC will be shorted, or you have to deactivate this DC source. So when this will be zero, so then what is going to happen? This R1 and R2 will come in parallel, and this RC will come with respect to ground. So it means that RE will be connected at the collector and the ground. So this is the you can see here, this is the AC equivalent model which we have drawn. This one is the R1 parallel to R2, and this one is the RC. Fine. So at high frequency, this capacitances exist. What I have already explained, that these are the stray capacitances, or you can say the internal capacitances, that is CBC, CBE, and CCE. Now in the now if you want to have the input side network and the output side network, for that you will have to split this capacitance into two components. So if you want to split this capacitance into two components, then you will have to use the Miller's theorem. Now, we have already discussed about the Miller theorem, but in short, I would like to explain this again. So now you see there is a black box, and this black box will be having a gain of V2 upon V1. So now this is the input port, there is the output port, and the impedance is connected between these 2 points. So if I want to split into this impedance into two components, then how I'm going to write? So you just indicate one current. So let us say there is a current flowing from this point to this point, and that current is having a value of I. Now similarly, you are having a current I dash. So how you can write I? It means that this point will be at the high potential, and this one will be at the low potential. So I will be equals to V1 minus V2 upon Z. So now you are replacing this V2 by AB into V1. So you can see V1 into 1 minus AB upon Z. And so if you want to have the impedance, then how you are going to write? You see, this is the current, this is the input voltage, and now we have to find the effective impedance, because we have resolved this impedance into two components. So one component will be at the input port, and the other component will be at the output port. So the effective impedance will be Z1 will be equal to Z upon 1 minus AB. But now here we are having only the capacitance. So when you are having the capacitance, then how you are going to write? You can see here C1 will be equal to C into 1 minus AB. So this one is the Miller input capacitance. Now similarly, you can evaluate the Miller output capacitance. So once you have evaluated Miller input capacitance and Miller output capacitance, then you can easily have the input side of circuit and the output side of circuit. So now what we have done, we have replaced this transistor by the RE model, like beta into RE and beta into IB. I think this one is clear to you. Then you are having R1 parallel to R2. You can see R1 parallel to R2 will be there, and the RC is there. So RC is connected between the collector and the ground. Okay, so now then you will have to place the capacitance. This is the diffusion capacitance. This one is the Miller input capacitance. Just now we have evaluated, and there is a wiring capacitance. So because ultimately you are going to put a wires, and you will connect a transistor into the system. So you will be having this wiring input capacitance and the wiring output capacitance. So this is the circuit. I don't think there is any doubt in this input side network and in the output side of network. So basically, now what is our next step? So our next step is to find the cutoff frequency, that is FH. So first you will have to find the FH for the input side network and the output side network, and then you will have to take the minimum of it. So why we have taken the minimum? Because you can see here in this gain versus frequency curve. Now if you are going to take select this value, if you are going to select this value, then at this frequency the gain will be minimum. We want to have the finite gain for all the frequencies. So that is our main intention, and therefore we will have to take the minimum of the FHI and the FHO. Now this is the cutoff frequency for the input network, and this is one is the cutoff frequency for the output network. So I have taken the two frequencies, and I want to prove my point that if FHI will be equals to 2 megahertz and FHO will be equals to 100 kilohertz, then I think you will have to select the 100 kilohertz as the cutoff frequency. So I think this is clear to you. So now we are having one problem, and we'll try to understand the high frequency analysis using this problem. So this circuit is there. Again, there is a voltage divider circuitry, and we are having this blocking capacitors and the bypass capacitors. These are the externally connected capacitances, and this is required if you want to amplify the weak signal, because ultimately your microphone is going to capture the weak signal, and we will have to deliver that signal to the speaker. So ultimately you will have to do the amplification. So the first stage will be the voltage amplification, and that will be represented by this circuit. So now you are having the transition capacitance. Now what is a transition capacitance? Transition capacitance is a capacitance between the collector and the base. Now similarly, diffusion capacitance is the capacitance, or you can say a straight capacitance between the base and the emitter. And there is also one more capacitance, so that is the 4 picofarad. It is between the collector and the emitter. So you can just go through these values. So what we have observed that the collector to emitter capacitance is very small, and this you will have to split using the Miller theorem. So first we will have to find the DC analysis. Now why DC analysis is required? Because if you have just seen in the AC equivalent model, or you can say high frequency model, there is a beta RE, and RE will be equals to VT upon IE. So if you want to find the IE value, then you need to uh, then you need to have the DC analysis. So in that case, so when you want to do the DC analysis, so that time your blocking capacitors will be open circuited, your bypass capacitor will be open circuited, and the stray capacitance will also get open circuited. So in that case, now you are having only this DC source. So the simple voltage divider circuitry is there. So in that case, how you are going to solve this? So what we will do, if you have just gone through the voltage divider network, and if you have done the analysis of the voltage divider circuitry, so we have done some Thevenin type of voltage, and the Thevenin impedance was there. So how to calculate VTH and the RTH? So VTH will be equal to simple R2 upon R1 plus R2 into VCC, and you have obtained this value, that is 6.37 volt. Now similarly, this one is R1 parallel to R2. So 22 kilo ohm parallel to 47 kilo ohm, that will be 14.98 kilo ohms. So after that, you will be having you will have to apply the KVL in the input load. So in that, if you solve this, the equations are very simple to solve. Then you will get the value of IB. So now, as you know that IC will be equals to beta into IB, that will be 1.526 milliampere. And in the common emitter configuration, IE will be equal to what? IB plus IC. As IB is in microampere, so we can easily neglect the base current value. So in that case, IE will be equal to IC. So that will be replaced by IE. So we can simply have this VT upon ICQ. Now how this VT comes into the picture? Now you know that VT means what? Thermal voltage, and thermal voltage will have a formula of KT upon Q. K means Boltzmann constant, that is 1.38 10 to the power of minus 23 joule per Kelvin. Now that T will be the absolute temperature in Kelvin, so that will be 273 plus um, 273 plus 27, that will be 300 Kelvin, and Q will be charge of an electron. So if you can simply put all the values, then you'll get the RE will be equal to 17.04 ohm. So now by doing this, we have got the RE value. So this is okay. Now if you want to find the Miller input capacitance and the Miller output capacitance, so you need to find this AV. AV means what? Voltage gain. So to find the voltage gain, first you will have to do the AC analysis. So in the AC analysis, we will have to neglect these capacitances. Neglect capacitance means what? You will have to short the capacitances. That is the externally connected capacitance I am saying. I am not saying the stray capacitances. Fine. So in that case, this will be a simple circuit, that is beta into RE, beta IB, RB is there, RC is there. So how you are going to find? We have to find the voltage gain, and voltage gain will be V0 upon VI. Fine. So how to calculate V0? So V0 will be equals to what? Current into resistance. So what is the current flowing into this? That is a beta into IB. So what we can say, beta into IB into RC. Now you can see this current is going in this direction, that is from top to bottom. And for voltage, uh, and how you are going to obtain the voltage? So voltage will be equals to minus beta into IB into RC, because this current is going from top to bottom, and if you want to have the positive voltage, then the current should flow into the RC. It should not go away from the RC. So in that case, it will be minus beta into IB into RC. And now here, what is the input voltage? You can see here simple base current is going to flow through the beta into RB. So that will be minus beta into IB into RC minus beta into RE into IB. So if you solve this, then you will get the minus 469 uh, value, and that will be your voltage gain. So I think up to this point, everything is clear. So now you can simply do the high frequency analysis. So now we will have all the capacitances. See, we have not incorporated any coupling capacitors and the bypass capacitor. We have just incorporated only the stray capacitances, the Miller input and the output capacitance, and the wiring input and the output capacitance. So first, as you know that we will have to find the Miller input and the output capacitance, and basically the that capacitance is from base to collector. It means that base to collector capacitance will be resolved into two components. The first one is the input component, and the second one is the output component. So for input, what will be the formula? Just now we have seen, so CMI will be equal to CBC into 1 minus AB, and this one will be CBC into 1 minus AB minus 1, or you can say inverse. So this is the transition capacitance that will be given. So if you just put down all the values, you will get CMI will be equals to 5.69 nanofarad, and CMO will be equals to 12 picofarad. So you just put this value. This is the wiring input capacitance. It is already given there. And CBE, this one is the diffusion capacitance. This is the capacitance between the base to emitter, and this is going to exist when you apply a forward biasing to the base and the emitter. Fine. Now, if you just find, uh, okay, so the input side will be there, C will be equal to water. So you can see all these capacitors are in parallel. These capacitances are in parallel, so you just have to add all the capacitances, that is C pi plus CWI plus CMI. So when the capacitances are in parallel, it means that you will have to add all the capacitances. So when you add all the capacitances at the input side, so you will get the value as 5.705 nanofarad. Now similarly, you will have to find the equivalent resistance also. So now you can see here RB and beta RE both are in parallel. Both are in parallel. So in that case, it will be, if you do the mathematics, then you will get the value as 1.52 kilo ohms. Now, FHI will be equals to what? 1 upon 2 pi into R into C. You have calculated the input, the effective input capacitance, then the effective input resistance also there. So you can simply put down all the values and you will get the input side frequency as, input side cutoff frequency as 18.35 kilohertz. Now, similarly, if you do the same thing at the output side, you will get 984 kilohertz. Now, you will have to take the minimum of it. You have got two values. The first one will be at the input, then this one will be FHO, or you can write FH2, no problem. Then that is 984 kilohertz. So you will take the minimum of this, and that one will be 18.35 kilohertz. So it means that beyond which, if you operate your transistor, your gain is going to reduce or gain will decrease, and up to this gain will be constant. So this is the check on your high frequency operation of the BJT. This is all about for the high frequency analysis of the BJT. So if you are having any queries, then please do message me. Thanks a lot.